So we're going to go ahead and take a look at thermodynamics. So the first law of thermodynamics states that energy cannot be created or destroyed. The reality of that is that energy is just exchanged or converted into different forms, and the reality of it is that energy, the energy of the universe is actually constant. And we've looked at this before in previous chapters, but the change in energy in a specific system is going to be related to Q and W. So the internal energy of that system is going to be based on heat changes as well as work changes. Okay, so remember Q equals the heat that's gained or lost, and work, W is work done to or by a system. And we talked about Q. When Q is greater than 0, we know that the system is going to be absorbing heat from the surroundings. When Q is less than 0, we know it's going to be releasing heat to the surroundings. When W is greater than 0, the surroundings are doing work to the system, so like a piston compressing. And when W is smaller than 0, we know that the system is doing work to the surroundings, so the rising of that piston upon the expansion of a gas or something of that sort. So let's go ahead and look at an example where the first law of thermodynamics creates a point of confusion. Okay, so if we go ahead and we look at this combustion reaction of methane gas, okay, we end up getting CO2 and H2O. We get an enthalpy value, a change in enthalpy value of negative 890.4 kilojoules. Okay, so basically what's happening in this reaction is that the potential energy that's stored in the bonds of our reactants is released as heat, as we see here with the negative delta H sign. Okay, so what we know is that the potential energy that's stored is now converted into heat energy, and we could obviously harness that energy and utilize it to perform work. But the reality of it is that the energy that is here shows up as heat being released in the reaction. Now, the first law of thermodynamics allows us a bookkeeping procedure or bookkeeping idea. So the idea that the amount of energy is constant and that energy is not created or destroyed but only converted allows us to determine the flow of heat, like the direction in which it's going to go, the form of the energy that's going to be assumed, potential energy, kinetic energy, okay, work, and also the quantity of energy in the change. However, the first law of thermodynamics only allows us this bookkeeping. It doesn't actually tell us why a reaction proceeds in a specific direction. We don't know why, based on the first law of thermodynamics, we don't know why this reaction proceeds in the direction that it does. Okay, and basically this unit is going to allow us to figure out why specific reactions move in the direction that they do. Okay, so in order to have this discussion about why reactions occur, and why they occur in their specific direction, we need to talk about a few things. First, we need to talk about spontaneous processes, and then we need to discuss something called entropy. So spontaneous processes are ones that occur without outside intervention. Okay, so basically they just happen. It just is. We take it as fact. Okay, and spontaneous reactions or spontaneous processes can be either slow or fast. The rate of that reaction, of course, is going to be determined by kinetic factors such as activation energy, temperature, concentration value, as well as the presence of a catalyst. And we've already looked at these kinetic factors in previous units. Okay, but the fact that it's spontaneous has nothing to do with the rate at which it occurs. Okay, so what thermodynamics is it's the focus on the initial and final states and basically ignoring the pathway that is studied by kinetics. Okay, so what do I mean here? Okay, if I look at this reaction progression here, okay, I'm going from reactants to products in this progression that we see here. We have our energy value here. Okay, and basically as we start with our reactants, obviously we're going to go through some reaction pathway. There's going to be some activation energy associated with this process. Okay, and then you're going to produce your products. Now, Kinetics focuses on this area of this reaction progression. It focuses on the activation energy, how the catalyst affects the activation energy, how your concentration or temperature will affect the rate at which this reaction occurs. Thermodynamics, on the other hand, only focuses on the final and initial states. Okay, they're state functions. They don't. It doesn't really matter the pathway which the reaction proceeds by. All that matters is the initial and final states when we're looking at thermodynamics. Okay, so spontaneous processes, they just happen. They do what they do. Okay, they occur in one direction. Okay, the direction that is spontaneous is the one that just occurs on its own. And generally speaking, the reverse of the spontaneous process direction is going to be a non-spontaneous reaction. So basically, some specific conditions or energy, things of that sort, must be added in order to get the reverse reaction to occur. Okay, temperature and pressure are usually important for determining if a reaction spontaneity, and we'll talk about how that comes into play in a little bit here. Okay, so let's look at the spontaneous processes and how temperature and pressure may affect these types of things. Okay, so spontaneous process, a great example is, I set a ball up on top of the hill. Okay, if I put the ball on top of the hill, it's possible for it to just eventually roll down the hill and do its thing. That reaction progression is very natural. On the other hand, if I put the ball at the bottom of the hill, it's never going to just roll back up on its own. The rusting of steel is another example. If we expose, a steel beam or something of that sort to air and moisture, you're going to have that iron turn into iron oxide. And that process, that just naturally occurs. That's what we see happen to bridges and things of that sort. Now, the reverse of that process is taking that iron oxide and breaking it back down into the iron metal and the oxygen gas. Okay, but the reality of it is if, I have that piece of rusty metal and I watch it, we notice that there really isn't a change in terms of that steel, that rusted steel or that iron oxide going back to the nice, beautiful, solid iron metal and oxygen gas. Okay, so notice the forward process is spontaneous, it just happens, but the reverse process is not something we see happen. Okay, a gas filling its container uniformly. We know that gas, if we open up a gas container, it's going to fill whatever room it's in or whatever container it's placed in. Okay, and it's going to distribute evenly throughout the container. So we know that the oxygen, for instance, that we breathe, that's inside the air mixture in a classroom or in our atmosphere. We know that the oxygen distribution in a classroom is going to be even throughout the room. We don't just have pockets of oxygen gas and the rest of the people on the other side of the room not being able to breathe. Okay, so that spontaneous mixing is a spontaneous process, and the reverse process, the isolation of those gases, is something that doesn't just happen on its own. It has to be forced. Okay, heat flowing from a hot object to a colder one. Okay, we know that if we stick our hand on a hot stove, that the hot stove is going to transfer that heat energy into our hand, and obviously we'll be in a little bit of pain. Okay, so that process is the natural progression or the natural flow of things. The opposite is not true. Okay, can't transfer coolness to the hot object. It's always the hot object transferring its heat energy to the cooler one. Okay, wood burning to form CO2 and H2O. Okay, those are the products you get during the combustion of that wood, but we can't take CO2 and H2O and expect it to be heated and subsequently give us a new log of wood. Okay, so once again, another example of a spontaneous process that doesn't have the reversible setup. Okay, in this case, temperature difference. So below 0 degrees, water is going to freeze. Okay, that it's spontaneous below 0 degrees for water to freeze. If we're above 0 degrees C, ice is going to start to melt, and so it's spontaneous at above 0 degrees C for ice to melt. So obviously, temperature is going to affect that distribution and what determines the spontaneity of this specific process, whether water's freezing or it's ice is melting. So basically we could see these examples of spontaneous processes. I think we understand these intuitively. These are things that happen, and we understand that. So now let's go ahead and look at how enthalpy, or if enthalpy, affects the spontaneity of a reaction. Okay, now all of these are examples of spontaneous reactions. Okay, and these are all of the enthalpy values associated with each process. Okay, and some of these have enthalpic values that are negative, so basically we have heat energy being transferred to the surroundings. Okay, and we have spontaneous processes that have positive enthalpy values, which subsequently means that the heat is being absorbed from the surroundings. So the reality of it is that we have spontaneous processes here. This is what happens. This is what they do. Okay, and they all have varying enthalpy values. Okay, so the reality of it is that enthalpy is not going to be the thing that's dictating, okay, or the only thing rather that's dictating the spontaneity of a reaction. Okay, so what gives? Okay, so the common characteristic amongst the reactions we just looked at is an increase in something called entropy. Okay, and entropy is the common factor to all spontaneous reactions. And entropy, which we represent by the capital letter S, is a measure of disorder. Okay, so basically, you know, like your bedroom, right? It probably has socks and shoes and maybe some homework papers and things of that kind of strewn about. Okay, there's disorder there. Okay, playing cards, if I take it out of the packet and drop it on the floor, they're going to randomly orient along the floor that I dropped them on. Okay, so entropy is the disorder of your substances or of your reaction. So the change in enthalpy can be calculated by taking the final enthalpy value and subtracting the initial enthalpy value. If I have a change in enthalpy that is greater than 0, that means that my entropy increases. So a positive enthalpy value corresponds to a increase in entropy. A negative delta S, or a negative change in enthalpy, is characterized by an entropy decrease. Okay, so spontaneous reactions are going to be dictated or driven by this entropic property, this disorder that occurs. So let's go ahead and let's look at some examples of processes that have positive changes in entropy and that are subsequently spontaneous. So we know that as we go from a solid to a liquid to a gas, we know that each one of these phases have different spacing and different, degrees of freedom. So we know a solid is going to be a lot more organized. The atoms are in close proximity and they kind of fit in a nice organized pattern. As we go from solid to liquid, okay, that organized pattern gets broken up and those atoms are able to slide past one another. There's more degrees of freedom here. And as we go from liquid to vapor, obviously we know that there's more particle spacing, there's more movement that is allowed. And so basically, as we go from the more ordered version to the super less ordered version of the gaseous state, we see an increase in entropy. Okay, and this process, okay, this vaporization process is going to be spontaneous. Okay, now when I have a solute and a solvent that I'm adding together, the solvent is going to be interacting with itself, the solute is going to be interacting with itself. But as a solution starts to be produced, we break up the organization that's seen here and here in the solvent and solute when they're by themselves. Okay, so a solution is going to have more disorder. You're going to have these solute particles randomly distributed in the solvent particles, and you subsequently get a solution. In this case, your change in entropy is going to be greater than 0. You're becoming more disordered. Okay, and typically a system where you have a low temp and then moving to high temp, okay, so basically adding heat, a lot of times if we increase the temperature of a system, particles are going to start moving faster. There's going to be increased spacing like we saw here with the solid to liquid to gas phase changes. Okay, so typically if we have a system at low temp and then we move it to a higher temperature, usually there's going to be less order, okay, or more disorder, however you want to look at it, and your entropy is going to increase. So these are all examples of processes with positive entropy values and subsequently things that we inherently know are going to occur spontaneously. Okay, so what is important with respect to the entropy values? All right, so the number of arrangements that you can possibly have is important. So basically, the more arrangements or positions or energy levels that are available to a specific system, the greater the likelihood of that event occurring. Okay, so if we look at these examples here, right, we have 3 different arrangements. Okay, we have arrangement 1, 2, and 3. And in each of these arrangements, we have different distributions of the colored balls. So in arrangement number 1, we have all the balls on one side. In arrangement number 2, we have all the balls, or 3 balls on the left, 1 ball on the right. Okay, and in arrangement 3, okay, we have 2 on the left and 2 on the right. Okay, and based on colors, we're assuming that each of these are, different atoms, okay, or different molecules, what have you. In the first example, there's only one microstate or one arrangement that's possible for that specific system. Okay, in example 2 or arrangement 2, there's 4. Okay, arrangement 3, there's 6. Okay, so the probability of this arrangement 3 occurring is going to be more likely because there's more microstates or there's more possibilities for it to be satisfied. Okay. So because there's 6 opportunities to satisfy the 2 and 2 arrangement that we see in arrangement number 3, it's more likely to occur than the 3 and 2 example that we see in arrangement 2 or the 4 and 0 example that we see in arrangement 1. So the number of arrangements possible is going to be important. The more arrangement opportunities you have or possibilities, the more likely that's the process that's going to occur. Okay, so another way to look at this is I guess from a mathematic perspective. Okay, so given a specific number of molecules, the probability of finding all of the molecules in this left-hand bulb over here is going to be affected by the number of molecules that are in the container, right? Okay, so if I have one molecule, I have a 50-50 chance of finding the one molecule on the left-hand side over here, okay? So basically the probability of finding that single molecule on the left-hand side would be, 50-50. If I add 2 molecules, right, okay, the probability of finding both of those in the left-hand side bulb is 1/2 times 1/2 because they both have a 50-50 chance of being in the left-hand side of the container. So that's going to give me a 1 in 4 chance of actually achieving that orientation. Okay, and as you continue down and add more and more molecules, the probability of finding all of those molecules on the left-hand side gets smaller and smaller or more and more remote. Okay, so it is more likely to have a randomization in a container as you add more molecules. So there's less likelihood of having that single perfect arrangement as you increase the number of particles. Okay, another thing that affects the entropy are molecular motions. Okay, so at the molecular level, how those structures are oriented with respect to the atoms involved in bonding, as well as their movement opportunities. So translational motions are actually directional movements. So like moving through a container or moving through space. Okay, so translational motion. Okay, the more translational motion you have, the more movement that you can do from one side of a container to another, the more entropy you have. Okay, vibrational motions are basically motions in a molecule as the atoms in the molecule actually move towards or away from each other. Okay, and these can be represented very nicely here. We have these hydrogen atoms moving away from the oxygen atom. We have one hydrogen moving away from the oxygen, one moving towards. Okay, we have basically a bending motion where both of these hydrogen atoms are moving towards and away from each other. Okay, so these are examples of vibrational motion. Okay, and rotational motion is just basically how the molecules can spin around a specific axis. So that's represented here. Okay, so obviously the more movements you have, or the more possibilities you have with translational, vibrational, okay, or rotational motion, are all going to be geared towards the more disordered situation. So the more degrees of motion you have, the more entropy you have, so the more favored that would be. Okay, so let's look at some examples. Which example has the highest positional entropy? Okay, so if we look at solid CO2 or gaseous CO2. So what we should think about is, first of all, these are the exact same molecules. Okay, so with respect to the types of bonding and stuff, that's, you know, pretty consistent. The difference here, though, is the proximity of the actual molecules themselves. So in solid CO2, the CO2 molecules are packed in a nice, organized, you know, solid structural pattern, you know, okay? But when we're talking about gaseous CO2, we know that those particles are going to be, you know, far apart. They're going to basically not be interacting as strongly as the solid CO2. So we know that there's going to be a greater distance between the CO2 molecules in the gaseous state, okay? And we also know that because there's a greater volume and a greater ability to move around through the container, we know that there's going to be more available positions and subsequently more disorder in the gaseous state than in the solid state. Okay, so N2 gas at 1 atm versus 0.01 atm. Okay, so the N2 gas, right, it's the same. Okay, they're both in the gaseous state. The difference here, though, is the pressure. Okay, so the 1 atm is a greater pressure than 0.01 atm. As we increase pressure, we push molecules or atoms closer together. So the example here at 1 atm are going to, those gaseous particles are going to be closer in proximity than the example at lower pressure. Okay, so at a greater volume, right, at lower pressure, that means that those particles are more free to move around, more free to, you know, spin around, rotate, okay, translationally move through the container. So that subsequently means there's more positions available, there's more disorder. So we expect the N2 gas at 0.01 atm to have the higher entropy value or more disorder. Okay, so if we look at a couple of examples and correlate it to our delta S again. Solid sugar dissolved in water to form a solution. Okay, so in this case, guys, we're taking nice crystalline organized sugar molecules that are in the solid state, right? And we're adding them to nice organized water molecules that are interacting with each other. All right, so there's order in both the solvent and the solute. When we put them together, we know that those two randomly mix, right? They actually dissolve. The water dissolves the sugar molecules. So in that case, we're going from the nice ordered water and the nice ordered solute to a more disordered solution. So we know that the entropy of that solution is going to be greater than the solid sugar and water by themselves. So we know that our delta S value is going to be greater than 0. It's going to be positive. Okay, and we know that because those sugar molecules are going to randomly pass through and orient inside the water molecules, and basically you're going to have more access to a larger volume, there's going to be more positions available, and more disorder in that system. Okay, now iodine vapor, okay, condenses on a cold surface to form crystals. Well, in this case, we're going from the gaseous state to the solid state. Okay, so anytime we go from a gaseous state to a solid state, we know that we are decreasing that volume, right? We're making it where the molecules are in closer proximity to each other, and basically there's fewer degrees of freedom. There's less translational movement, there's less rotational movement, vibrational movement, etc. Okay, so this process of going from gaseous iodine vapor to solid is going to exhibit or show a decrease in entropy, right? It's going to become more ordered than it previously was. Okay, so smaller volume, okay, is going to lead to that decrease in entropy and subsequent fulfillment of more order or less disorder, however you want to look at it. Okay, so another couple examples, a few examples rather. Okay, so in the pairs below, we want to choose which situation has the greater entropy. Okay, so In this case, we have 1 mole of sodium chloride solid and 1 mole of gaseous HCl. So in this case, guys, we're talking about a solid versus a gas. Okay, anytime you have something that is has more volume, has more translational moments or opportunities, that basically are going to have a higher entropy or higher disorder degree. Okay, 2 moles of HCl versus 1 mole of HCl. Okay, the 2 moles of HCl are going to have more translational, more vibrational options and opportunities. So having more molecules or more moles of HCl are going to lead to a greater degree of disorder. Okay, in this example here, it's 1 mole of HCl versus 1 mole of argon. Okay, so they're both in the gaseous state, right? So we're comparing them we're comparing them directly because they're both in the gaseous state. So theoretically, they have the same, translational ability to move through that container or around that container. However, argon is a single atom all by itself, so it doesn't have any of the stretching or bending motions that we discussed with respect to those vibrational modes. However, HCl is a molecule, okay, and basically has the ability to, have different movements than the argon. So HCl is going to have the higher entropy because there is another degree of motion or movement or disorder that's able to be categorized versus the argon, which has the translational and rotational, but doesn't have those stretching or bending vibrational modes as the molecule does. So now that we have an understanding of entropy and what it is and what it means with respect to disorder and things of that sort, let's go ahead and look at entropy in the second law of thermodynamics. So the second law of thermodynamics states that any spontaneous process, there is going to be an increase in entropy of the universe. Okay, so spontaneous processes are going to make the entropy of the universe increase. Okay, and the entropy or the change in entropy of the universe is going to be equal to the change in your system and the change in your surroundings, summed together. So if my delta S of the universe, or my change in entropy of the universe, is greater than 0, that process that I'm looking at is going to be spontaneous. If it is equal to 0, the reaction is not going to really have a tendency to occur, or at least it's going to be at equilibrium. Okay, and if it's less than 0, then the spontaneous reaction is actually the one that's occurring in the opposite direction. So the reverse process is going to be spontaneous in that situation. So let's go ahead and redefine system and surroundings, and just to make sure that we're understanding what we mean by each of these. Okay, so the system is that area or that reaction or that process on which we focus our attention. Okay, and the surroundings are everything else in the universe. So the universe entropy is going to be related to the sum of the system and the surroundings, give and take that occurs. So we know enthalpically, when we're talking about heat transfer, okay, we've discussed this, but in exothermic processes, we know that the system gives off heat to the surroundings. Okay, we know that that is an exothermic process with respect to heat values. Endothermic processes, we know that the system absorbs heat from the surroundings and subsequently takes on that energy from the outside. So let's go ahead and let's look at the change in enthalpy of the universe for a specific reaction and discuss how the system and surroundings are going to dictate the features of the overall change in the entropy of the universe. Okay, so if we look at H2O going liquid going to H2O gaseous state, or H2O in its gaseous state, we are going to first of all identify what is the system. So in this case, water is the system. So everything else is the surroundings. Okay, so that's the first thing we have to indicate. Okay, now some things to think about with respect to our system is that the change in entropy of your system is going to be dictated by those positional probabilities that we have discussed. Okay, so position in this case is going to be what dictates whether this is positive or negative. Okay, and so if we look at that, we are going from a liquid state to a gaseous state for this substance. So we're going from a more ordered to a more disordered state. So our change in entropy of our system, okay, is going to be positive in this case. Okay, and this makes sense because, you know, even if we looked at this calculation-wise, okay, if we looked at the volume associated with liquid water versus gaseous water, okay, there's a whole lot more volume in the gaseous state, and so subsequently you have more volume, you have more positions for the water molecules to move through the container, and subsequently the change in entropy of your system with respect to positional probabilities or positional considerations is going to be a positive value. Okay, so, and we know that this delta S of universe is equal to the delta S of your system and the delta S of your surroundings. Okay, so now that we've looked at the delta S of the system and considered those positional considerations, let's go ahead and look at the delta S of the surroundings. Okay, so the delta S of the surroundings is going to be determined by the flow of energy into or out of the system. So depending on if you have an exo or endothermic process, that's going to dictate the delta S value of your surroundings. Okay, so if the process is exothermic, obviously we are releasing heat to the surroundings, so that's going to cause more disorder in the surroundings. So our entropy value will be positive for the surroundings in an exothermic process's case. Okay, and the opposite is true for an endothermic process. All right, so going from H2O liquid to H2O gas is an endothermic process. The system is absorbing heat from the outside. So we know in this case that our delta S of our surroundings is going to be less than 0. Okay, so now that we have our generic values here, okay, we know that relatively speaking, one's positive and one's negative, we have to figure out values that are associated with these delta S of the system and delta S of the surroundings. And so what's going to actually dictate whether we have a positive delta S of our universe or negative delta S of our universe is really going to be dependent on temperature, okay? And basically the delta S of your surroundings is related to the enthalpy of your reaction and the temperature. So enthalpy and your temperature. Okay, so basically the impact of the heat transfer to the surroundings is going to be more dramatic or have a larger effect the lower your temperature is, right? So let's go ahead and look at how this comes into effect. Okay, so this problem right here tells us to calculate the delta S of surroundings for the following reactions that are all at 1 atm and 25 degrees C. Okay, so in this process, the enthalpy value for this replacement reaction is going to be negative 125 kilojoules. Okay, so we can calculate our delta H of surroundings by plugging in our enthalpy value into this equation here, okay, and dividing by our temperature of the system, okay, at 25 degrees C, but of course we convert it to Kelvin. Okay, we divide those two together, and in this case, our enthalpy of surroundings is going to be a positive 0.419 kilojoules per Kelvin. Okay, so in this case, this exothermic reaction causes an increase in the disorder to the surroundings, so your S for your delta S of your surroundings is positive. So entropy is going to increase in that example. Okay. In this example here, we have an endothermic process. Okay, so heat is being taken from the exterior of the system, the surroundings. Okay, we plug those in just like we did here. So in this case, the delta S of your surroundings is going to be a negative value. Okay, and so in this case, if the delta S is going to be a negative value, the disorder is going to be decreasing in the surroundings. So how do we decide if the process is going to be spontaneous or not? Well, we look at the delta S of the system and the delta S of the surroundings, okay? And if we know their relative signs and, of course, their sizes, then that's going to help us dictate if we have a spontaneous process or not. So in the case of both the system and the surroundings entropy values being positive, we know that the change in entropy of the universe will be positive, and so causing more disorder is going to cause that reaction or that process to be spontaneous. Okay, if both of them are negative, that's going to give us a negative delta S of our universe. Okay, and so this reaction direction that we're looking at will not be spontaneous, but the reverse process will be. Okay, now in the case where we have a positive and a negative, whether it's system or surroundings, that's going to be dictated by the relative size of the entropy value associated with our system and our surroundings. Okay, so remember we utilize enthalpy values and temperature, okay, to figure out our delta H of our surroundings. So that's going to be a way in which we can calculate our entropy of our surroundings. So how do we figure out or deal with the entropy changes of the system? Okay, now this brings us to the third law of thermodynamics, okay, and basically we're going to talk about that, and we're going to talk about how this relates to the standard entropy of the system and figuring out those numerical values that we need to decide if our delta S of the universe is positive or negative, and subsequently if our reaction or our process is spontaneous or not. Okay, so third law of thermodynamics basically is looking at the entropy of a perfect crystal, so perfectly organized crystal at 0 Kelvin. Okay, so basically the entropy or the disorder of a perfect crystal at 0 Kelvin is 0. Okay, so theoretically, absolute 0. Okay, there is no disorder in that crystal. Okay, now the only way to have this is to have every particle in its place and basically perfectly organized. Now, as we increase the temperature of this crystal, we know that that increase in temperature is going to increase the vibrational motion, it's going to increase the spacing, it's going to basically overall increase the entropy. Okay, and so we can use this reference point of that perfect crystal to help us determine the standard entropy value. Okay, and the standard entropy value, okay, is represented by S naught, okay, as we see here. So the standard molar entropy is basically the molar entropies of a substance in their standard state, okay, and so at pressure 1 atm is where we measure these, and we reference them at 298 Kelvin. So basically standard molar entropies are going to be expressed in lots of charts and tables, okay, and they're usually listed in various appendices and things of that sort. Okay, but let's go ahead and let's look at what the standard molar entropy values are kind of dictated by. Okay, so the standard molar entropy of elements are referenced at 298 Kelvin. Okay, so that's where we make our reference points. Okay, the standard entropy values of gases are greater than liquids, which we would expect because there is more disorder associated with a gas typically than a liquid. Okay, there's more modes of movement, there's more translational, rotational, etc. Motions allowed. Okay, standard molar entropies are generally going to increase with increasing molar mass. So usually the more molar mass you have, you either have more atoms or you have more translational movements. Okay, and standard molar entropies also increase with increasing number of atoms. More atoms in the molecule, you typically have more rotations, more stretches, more ability for the molecule itself to move. So that is standard molar entropy. So in order to calculate the change in entropy of our reaction, we are going to utilize the standard entropy values from the tables that we've looked at previously. Okay, so this equation right here should seem very familiar to most of you guys. We've used them with the enthalpy values in the past. It's the same type of math. It's just instead of the enthalpy, standard enthalpy of formation values, we're going to be using the standard entropy values. So, okay, so basically it's products minus reactants. Okay, so the way that we're going to set this up is that the delta S naught of the reaction is going to be equal to the sum of the products. So we have 2 moles, Okay, and the reason why I know I have 2 moles is because the coefficient of 2 in front of SO2. So 2 moles of my SO2 times the standard molar entropy of SO2. Okay. Oops. Plus. Okay. Let's see, 2 moles once again for my NiO. Okay, and the value for my NiO is going to be 38 joules per Kelvin mole. Okay, plug those in. Okay, all right, so those are my products. Now we're going to subtract out the sum of my reactants. So I have 2 moles of the NiS. Okay, and that has a standard molar entropy of joules per Kelvin mole. Pardon me. Plus the 3 moles of O2. So times. Okay, so we go ahead and we plug all these in. Okay, notice that we have our products. Okay, so we have our products shown here. Okay, so these are our products. Okay, down here are our reactants. Right, so it's going to be products, the sum of the products minus the sum of the reactants, and that's going to give you your standard molar entropy. Okay, and this is actually expected. If we looked at this reaction in a generic way, notice that we start with 3 moles of O2 as our gaseous reactant, and we end up with 2 moles of gaseous product. Okay, so we would expect our delta S in this situation to be negative for the specific reaction. Why? Because entropy is decreasing, and that's what we actually see from the calculation that we've done here. This problem here, we're going to be using the same type of approach that we used in the previous examples. And we're going to be using the standard molar entropy values from the table of both our products and our reactants in order to calculate the overall change in standard molar entropy of this specific reaction here. Okay, so the same products minus reactants approach that we took on the last slide will subsequently give us our change in standard molar entropy of 179 joules per Kelvin. Okay, and if we were to have looked at this reaction generically, the delta S, right, we're going from 3 moles of gaseous product, okay, to 3 moles of gaseous product. So the molar amounts are the same. So in this case, we wouldn't have necessarily expected delta S not to be positive or negative. We would have expected it to be 0. And the reason why it isn't 0 will be discussed here in the next slide. Okay, but the calculation approach that you do here is the same that we did in the previous slide. It's products minus reactants. Make sure you're paying attention to the units and canceling out your moles that you're actually ending up with from each of the coefficients from the balanced equation. So the reason why that reaction doesn't have a standard molar entropy change of 0 is because of the types of gaseous product versus gaseous reactant that's present. Okay, so if we go ahead and we look at H2 versus H2O, okay, we have the same number of moles of each of the reactant and product. However, what you need to consider is that both of them are quite different. Okay, hydrogen only consists of 2 atoms, and there's only so many vibrational motions that are going to be possible when you have just 2 atoms. Okay, now in the case of H2O, notice that there's a big increase in the number of vibrational modes, okay, that are actually going to be allowed for this specific compound. So when you have more modes or more motion options, you're subsequently going to have more entropy. So the reason why we have a positive change in our entropy value is because of the features associated with the H2O molecule itself. So generally speaking, the more complex a molecule, the higher the standard molar entropy is going to be.